guys can hear me? Yeah. All right. Whoops. OK, good. So where were we? So for those of you who missed my first lecture, I'm just going to flash all the slides again. And I think you'll all absorb it instantly, so it's OK. OK. So what I did last time was I talked about a well-established duality transformation between an XY model in 3 dimensions, which models a superfluid, and a dual XY model, which is strongly interacting, which couples to a fluctuating vector potential, sometimes called as the abelian-Higgs model. And we talked about how we can understand the superfluid to insulator phase transition in the language of the original XY model, or the second, the dual abelian-Higgs model, and you get the same answers. Then lastly, what I told you was that you can understand the Goldstone mode of the original XY model as the photon in the dual theory. This is where I ended up. So to sum up all of what I said last time, we had a relationship between the supercurrents of the original XY model, capital J, and electric and magnetic fields of the dual abelian-Higgs theory. But it turns out that a similar relationship exists from the vortex point of view, the abelian-Higgs point of view. If you look at the vortex currents, which I'll denote little j, they're going to be related to the actual laboratory electric and magnetic fields, which I denote here. So for instance, the density of vortices is given by the magnetic field applied in the lab. That makes sense. If you apply a field, you'll nucleate vortices. The vortex currents are related to the electric fields. This is familiar from the idea of a phase slip. If you have a current of vortices going along x, it produces a voltage pulse perpendicular. Okay? And where that comes from is, if you look at the abelian-Higgs action, the fluctuating vector potential, little a, enters in 2 places. It couples to the matter fields, and it couples to the background A. And so whereas in the previous demonstration, I told you that from the XY point of view, to satisfy current conservation, a divergenceless current is a curl of something. That's how the fluctuating vector potential arises. Now I'm going to turn it around and say the vector potential, that vector potential which was used to satisfy the constraint, actually now acts as a Lagrange multiplier, which couples to the currents of the vortices and the electric and magnetic fields applied in the lab. So this constraint implies this relationship. Now this is important because what you see is that this duality transformation interchanges currents and electric fields. So that has consequence for linear response, right? Because we can define conductivities. The currents, there's going to be some conductivity times the electric field. The vortex currents can also be some vortex conductivity times the fluctuating electric field. But using the fact that the electric field is the vortex current and the supercurrent is the vortex electric field, you see that conductivities become resistivities. And in particular, the vortex conductivity is 1 over 4 pi squared times the electrical resistivity. And that's another way of seeing how the phase diagram gets inverted. If you think about the phase diagram in the original language, a condensate of vortices which has infinite conductivity is a condensate of the bosons, the original bosons, which has infinite conductivity, becomes an insulator of the dual particle, the vortex, which has an infinite resistivity, and vice versa. Now, in addition to having implication for response, there's also implications for symmetries. And this is also intuitively familiar. Because currents and electric fields get interchanged, we know that under a time reversal transformation, the currents flip. They go around the opposite way. So when you do that, a vortex becomes an anti-vortex. So in this representation, the electric fields, which were originally pointing outward to constrained by Gauss's law, now point inward. So a time reversal mapping changes a vortex into an anti-vortex. It's like a particle hole transformation in the vortex representation. The way you, whoops, oh, okay. The way you implement this is implemented explicitly by changing the sign of time. And what you want to do is preserve the sign of the external electric field, reverse the magnetic field. That's what time reversal actually does. But in the dual representation, it's the electric field that changes sign, and the dual magnetic field doesn't change sign. Okay? So this is called particle hole transformation, and this is called time reversal symmetry for the original particles. Okay, so I've told you about the boson-vortex duality. One thing that I'll come to later on is that this isn't unique only to bosons. You can also do this with fermions. You can have fermionic particles with currents in 2 dimensions, and they will also be dual to some fictitious electrodynamics, electric field and magnetic field. And their currents will also be related to some photon field, just like this. But in this case, everything will pertain to fermions. Okay? Now, it turns out fermionic vortices arise in our descriptions of the fractional quantum Hall effect. They're sometimes called composite fermions. Okay? I'll come back to this later. Okay, so if you recall my outline, let me go back here, flash back to the outline. This is part 2. There's 2 aspects of the dualities I wanted to cover: boson-vortex duality, and the second is boson-fermion duality. So now I'm about to come to the boson-fermion duality. Okay, now let me come back here. And what this is essentially making more precise, or in a statistical mechanics sense, more accurate, the notion that comes back from the quantum Hall effect era of flux attachment. Okay? So this is a cartoon from Dana Rovas's PhD thesis. You take electrons, you impart a singular gauge transformation, and you map it onto particles which have different statistics. Okay? And I'll cover that as we go along. But what I want you to take away is that we can think of the original electron as a boson plus a flux quantum, or vice versa. And this is the idea of statistical transmutation that we've had for a long time. But the recent developments has put this on a firmer footing in the language of statistical mechanics. And that's what I want to cover today. Now, given my time limitations, I want to say that there's 2 perspectives on this. There's a perspective of, you give me a microscopic many-body wave function, I will transmute the statistics of those particles. There's another perspective, which is from the point of view of the path integral. Okay? When I'm done with the lecture, a great question would be for one of you to ask me about the microscopic, how the microscopic point of view relates to the path integral point of view, because due to time constraints, I'm going to skip a few. I realized I went rather slowly last time. But from the path integral point of view, if you have electrons with some kinetic energy, and they're coupled to an external vector potential, and they have interactions, you can think of this problem exactly as a problem of bosons, which see, in addition to the external field, a fluctuating vector potential and interactions. And there's this last term, which is known as the Chern-Simons term. Okay? Epsilon mu nu lambda, a mu d nu a lambda. And sometimes people call this level 1 because the numerator here is I times 1. Okay? So whatever that integer that multiplies I is known as the level. Okay? And basically, it corresponds to how many fluxes, the inverse of how many fluxes you are attaching. So here we're attaching 1 flux quantum, and that transmutes to statistics from bosonic to fermionic and vice versa. And this fluctuating vector potential acts again as a Lagrange multiplier, but now it imposes the constraint of flux attachment, namely that the density of these bosons is 2 pi times, sorry, I have the 2 pi should have been on the other, no, this is right. Okay, so it's 2 pi times, so the flux of these particles, of this field, is 2 pi times the density of bosons. And 2 pi is, in our units, the flux quantum. Okay? And this type of thinking goes back to Xu Chang's original seminal insights in the quantum Hall effect. And for those of you who went to the colloquium, the this stuff was put in a broader context in a rather beautiful way. Okay. So here's the boson-fermion duality. We take these ideas of flux attachment, and we can extend them even to gapless points, critical points between quantum Hall states. Because what we're doing now is not quantum mechanics. We're not dealing with wave functions and attaching flux, but we're doing statistical mechanics. Okay? And so the statement of the boson-fermion duality is this. We have a boson. Okay? It's coupled to a dynamical vector potential, and it has a level 1 Chern-Simons term. Okay? That's the Euclidean action, Euclidean Lagrangian. It's dual to a Dirac fermion, which has some level half Chern-Simons for not a fluctuating vector potential, but a background capital A. This is how we implement flux attachment as a statistical mechanics transformation. But this second term here may be mysterious to you, and I want to demystify it just for the moment. So sometimes theorists use these fancy words called the parity anomaly. And what it is rather simple. You take Dirac electrons, Dirac fermions in 2 dimensions, say something like graphene, a spinless version of graphene. Whenever you have time reversal symmetry, you're required to have an even number of nodes, right? So like in graphene, you have K and K prime. So if you have a single massless Dirac fermion, you can think of that as starting from this, but giving one of its partners a mass. And you know, usually when we think of giving particles mass, at the scales below the mass, you think they don't really matter. But this is an exception to that rule, because this massive fermion generates a Hall conductance. So if you now put leads on this particular system of one massless Dirac fermion and a massive Dirac fermion, you find a huge Hall response, which is 1 over 4 pi, or in other words, E squared over 2h. And whether it's positive or negative depends on the chirality of the fermions, the sign of the mass term. So when we write this Dirac electron like this, it's fermions which are Dirac, but then they have this additional term. What we really mean is we have a single massless Dirac fermion on a lattice with a massive partner. Okay, so it's a well-defined lattice description. And if you have, the way this Chern-Simons comes about is if you have a massive Dirac particle, you can integrate it out. It's a gap degree of freedom. And when you integrate it out, you find that at one loop, you find this term, this Chern-Simons term. And there are no corrections to it from higher loop effects. Although there are corrections to the action for capital A at higher orders, this Chern-Simons term is completely one loop exact. And now if you have both Dirac nodes that are gapped out, the effective theory will have Hall conductance coming from this fermion and this fermion. And the total sum of the two masses, of the signs of the masses, is known as the Chern number. And that will become the level of the Chern-Simons term. Okay? The reason I tell you all this is because I'll be using it in a moment. Okay? So we have this boson-fermion duality, and we can understand the phase diagram just the way I talked about the boson-vortex duality. There's 2 phases, a superfluid and an insulator. But now, because of this extra Chern-Simons term, when the boson is gapped out, this describes an insulator. The same type of reasoning that I talked about last time will lead to that conclusion. But then when this particle condenses, in the ordered phase, it gets a non-zero expectation value. The fluctuating vector potential there's a Meissner effect. It gets pushed up. It becomes massive. And below the scale of the mass, we can ignore it wherever you see it. And then the effective theory, ignoring the matter fields and the fluctuating vector potential, is just 1 over 4 pi capital A d capital A. And this is the long wavelength description of an integer quantum Hall state. The reason it's an integer quantum Hall state is if you differentiate with respect to capital A, you get a current. And you can write the current as purely a Hall current. The current along x is related to the electric field along y, and the coefficient is 1 over 2 pi, which is E squared over h. Okay? So that's the integer quantum Hall state. So unlike superfluid to insulator, this describes a quantum Hall to insulator transition. Okay? Now, this should be fermion. We can see the same physics coming from the Dirac fermion based on what I told you before. There's two phases for this Dirac fermion, one where the mass is positive and one where the mass is negative. When the mass is positive, the half level coming from this Chern-Simons term cancels this one. And when it's negative, it adds, giving you the integer quantum Hall effect. Okay, so the phase diagram matches. The remarkable thing is that this duality transformation also holds when we're at the gapless point where this boson is massless and where this fermion is massless. Okay, so this is now some sort of continuum-like intuition. You might say like it's like a conjecture. One thing we did recently was to show that there's an exact lattice version of this duality at the level of the boson-vortex duality. And the way it works out is, since I don't have time to go through it step by step, I'll motivate the key steps. What we did was we put this boson-fermion duality on the lattice. And the way we did that was to have bosons on a lattice. We had a three-dimensional cubic lattice. And that was just an XY model, okay, living on the sites of the lattice. And this is actually a lattice gauge theory. So on the links of that lattice, we have this fluctuating vector potential. Now the question is, how do you couple Chern-Simons to those fermions, to those XY model phase variables? And you know, this turned out to be a rather tricky issue for a long time. People tried to put Chern-Simons terms on a lattice. They always violated gauge invariance. There were all kinds of subtleties. But based on what I just told you a few slides ago, it's kind of trivial. All you need to do is put Dirac fermions on the lattice. Because we know if massive Dirac fermions exist, they can be integrated out to produce a Chern-Simons term. So what we did was we have a lattice with XY model living on the sites, and also Dirac fermion fields living on the sites of the lattice. And you have a hopping problem of fermions. You have a hopping problem of the bosons. Now, because we're on a cubic lattice, there's going to be 8 nodes where the Dirac fermions live, 0, 0, 0, pi 0, 0, et cetera, et cetera. Okay? And each of these nodes will generate, if they're massive, they will contribute to the level of the Chern-Simons term. So schematically, the boson side of the duality was implemented by an XY model with a fluctuating vector potential coupled to Dirac fermions living on the lattice. By the way, I call this W because the first person to do this was Wilson, who was studying lattice gauge theory, lattice QCD. He put fermions in 4 dimensions on lattices, and he had an implementation on a Euclidean lattice. So we do something similar.
So the third dimension is time?
It's imaginary time, so it's really space. Yeah.
Is there some requirement that the mass is much less than the bandwidth?
Which mass and which bandwidth?
So the direct mass.
And which bandwidth?
The bandwidth of your lattice. You have a hopping Hamilton, so then that defines
The mass cannot be less than a bandwidth because you have a band. I mean, there's 2 bands at least, right? Say, there's an upper band and a lower band. The mass is by definition smaller than the bandwidth, which is the total spectrum. So I'm not sure what you mean.
Is there a requirement that the mass is much less than the bandwidth?
No, so I will tell you what we need to do. It actually depends on what you mean by mass. What you need to do is adjust microscopic lattice parameters such that the node at k equals 0, 0, 0, 0, the gamma point is massless, and other nodes are massive. Okay? So that's the only single 2-component Dirac fermion in the problem. And all the other partners add up to produce a level 1 Chern-Simons term. Okay? Sorry, that's on the other side. What we start with is give masses to all 8 nodes and choose it such that you can adjust the microscopic parameters such that the total level is 1. Okay? So this will become, if you think about it in the continuum representation, a level 1 Chern-Simons term. But it's coupled to the XY model through the gauge field. Okay? The Dirac fermions couples to the vector potential. The XY model couples to the vector potential. But the key is that they have opposite signs. Okay? So because they have opposite signs, they attract one another. Okay? Opposite charges attract, right? And so what you can do is you can do this integral exactly. Okay? You can integrate out the gauge field, and what that does is it glues the XY model degree of freedom to the fermionic degree of freedom. So before we did this, the XY model has bosons hopping on the lattice. Since they're bosons, you can hop 10 of them at a time, 100 of them at a time, it doesn't matter. But once you glue them to a fermion, you can only hop one at a time. The currents of the bosons become the currents of the fermions. And what we find at the end of the day is that you get a new composite particle, which is the product of the xy phase, e to the I theta, and the Dirac fermion that we use to implement Chern-Simons. Okay? And this is a fermion. And this becomes the free fermion, the free Dirac fermion on the dual side.
So we glue the boson and fermion together. Do one of those dominate the dynamics of what's going on?
No, because there's no Wick's theorem here. This is a strongly interacting problem. Even though the fermion is massless, when the boson when chi is massive, when the xy model is tuned to its critical point, this fermion is also gapless. So there's no factorization of correlation functions. Okay? So it's pretty neat that you could actually do this integral exactly. Let me just say that the exact mapping of partition functions maps an interacting problem onto an interacting problem. So in some sense, it's exact but useless. But you can play around with the microscopic implementations of the Dirac fermions to realize a free fermion on one side and a xy model plus level 1 Chern-Simons on the other. Okay? Yes, we preserve compactness. We do all of that. Yes, it's just a circle, e to the I theta, exactly. And you can do those integrals. There's a question back there. Sorry, can you repeat? Yeah. That helps us because we have 8 nodes, so we have an even number of fermions. And so the different nodes will produce contributions to the level of the Chern-Simons term that couples to the xy model. What do you mean they're not realistic? It depends on what you mean. So for condensed matter physicists, they're every bit as realistic, right? Because that's the band structure of the problem. It's just if you're focused on the gamma point, then you might say they're unrealistic because you want to take the continuum limit. But when you put them on a lattice, they're real degrees of freedom. You mean if it's massive? Or oh. No. We want to give those masses such that they produce Chern-Simons terms. If they were massless, they would be additional low energy degrees of freedom. That's true. Yeah, Oscar. Yeah, so on the quote-unquote free side, it's actually interacting, but you can adjust it such that it's free. But because it's a Dirac fermions, interactions are irrelevant, so it will flow to non-interacting. Yeah?
I have a related question. The parameter regime that the tuning of parameters you access that, is it just changing the parameters in the band structure?
Yes.
Change the lattice spacing?
No, just the band structure, the mass terms on the lattice. Yes. Okay, so that's good. So now we have two implementations of dualities on the lattice. We have the Boson-vortex duality and the Boson-fermion duality. Okay? So now what we're going to do is take a leap to show that these are members of a bigger web of dualities. Okay? All right. The way it works is the following. So if you have two theories that are dual to one another, you can generate new dualities by acting on each of them, which are what are called modular transformations. So if you have one theory, there are two modular transformations, and I'll explain what this means in a second. There's one modular transformation which is called S, which takes the original theory, and what it does is it takes the background field, it promotes it to a dynamical variable, and adds this cross term between the dynamical variable and a new background field. Okay? So that's called an S transformation. And then there's another transformation, which is called T, which takes the original theory and adds a level 1 Chern-Simons term for the background. And so when you start with one set of dualities, what you can do is operate on these two sides with some powers of s's and t's and do whatever you want and arrive at some new set of duality. And the claim is if the left-hand side represents a duality, the right-hand side represents a duality. Now, this second operation looks relatively innocuous, but this first operation is highly singular deformation. So it seems like you need to accept it on faith that S acting on two dual theories remains dual. But what we did, if I don't get to it, is we were able to implement these also on the lattice, because this looks like a Chern-Simons term, and we know how to do that now with fermions, so we can implement this, and then the web is the web I'm about to show you can be realized in principle on the lattice. So these are called modular transformations. The natural question you might ask is, why are they called modular transformations? And luckily, in the last talk, we heard some aspect of this. There's a group called the modular group, which takes a number z, complex number z, and does this transformation, where a, b, c, and d are integers. Okay? And this group has it's called PSL2z. I won't, unless someone wants to know, I won't say why it's P, but anyway. The two generators of this group take this number and invert it, so minus 1 over z. That is to say, b is minus 1 and c is 1. And then t, which is z goes to 1 plus z. Okay? So that would be a is equal to 1 and b is equal to 1. And d is equal to 1. So connecting this S and T to our S and T is done as follows. So if you want to interpret the linear response conductivities of some theory, take sigma xy plus I sigma xx and call this z. It turns out under S, the conductivity flips like this. And under T, the conductivity increases. Notice that only the real part increases. So the Hall conductance increases here, but the full conductivity tensor gets inverted under S. Okay? When you do this, you get a whole bunch of dualities that you could in principle realize on the lattice. So there's the XY model with a level 1 Chern-Simons. That's dual to the free Dirac fermion. That's the Boson-vortex, Boson-Fermion duality. I haven't shown you yet, but there's also a Fermion-vortex duality, which relates this to an interacting Dirac fermion. Then you can take this modular transformations and go to the XY model and show that this is dual to 3 other theories. Okay, so we're going to see this at a kind of cartoonish level. How much time do I have? In the next 8 hours, we will cover all these theories, but probably don't have that much time, right? 30 minutes? Yeah. OK, so just to give you some flavor for what this is, suppose you start with the XY model. If you act with it on S, what it does is it gauges this XY model. Okay, so big A becomes little a, and then we add this term. But what you notice is this is exactly the dual theory. So this is the vortex, the abelian Higgs Lagrangian. Okay, so this XY model becomes an XY model coupled to a fluctuating vector potential. So the S transformation converts particles to vortices in this case. But we can ask, what's the vortex of a vortex? So if we take this theory and hit it with S, we get S squared times the original. And when you do this, when you repeat this operation, you notice that there's a new fluctuating vector potential, which I'll denote little b. And it couples not to the matter fields. It only couples to little a and big A. And it acts like a Lagrange multiplier, setting little a equal to minus big A. And so when you do that, you find that you get back the original XY model with minus a. This is somewhat important in my discussion, because what it says is that if you go from the original superfluid variables, S takes you to the vortex variables. But now if you are an alien who thinks only in terms of vortices and not the superfluid degrees of freedom, if you ask what's the vortex of my vortex, it's the original superfluid variables, but up to a charge conjugation. Okay? And that sort of makes sense from this, because S is this operation. When you take it square, you get a minus 1. from this modular representation. Okay, so we can play this game many, many times. We can start with the Boson-Fermion duality and act on it with a set of these modular transformations. And what you get is, when you do it on the left-hand side, you get back the original XY model. I'm not telling you how you show this, but the calculations are trivial. They're just literally finding some Lagrange multipliers and satisfying constraints. Okay? So you find the original XY model on one side, and on the right-hand side, you find a Dirac fermion, which is coupled to a level 1 Chern-Simons term. So what we've done is, we had shown on the lattice an exact duality between a boson. Can you say it in the language of flux attachment? You attach flux to a boson, you get a fermion. But when you do this, you get a new duality, where we get a boson on one side and a fermion plus flux quantum. So that's not surprising, because just because you can think of a fermion as a boson plus flux quantum, you can also think of it vice versa. So if in effect, we move the Chern-Simons term on the other side. Okay? So I call that fermionization from bosonization. Now, one neat thing about this is that in this rapid-fire tour of these duality webs, you notice that one theme that recurs is that the notion of symmetries can be hidden sometimes. So one example of this is, take the duality between the XY model and this Dirac fermion, okay, plus a flux quantum. The XY model is time reversal symmetric. Okay, let's suppose there's no external magnetic field. But on this side, it looks like this fermion has a flux quantum, so it looks like it breaks time reversal. So if I were to compute the Hall conductance of this theory in my favorite approximation, say RPA or something, I would conclude that this has a huge Hall conductance, but it should actually be 0. So how do we relieve that paradox? Well, what we do is we go back and act on both sides with this time reversal transformation that I alluded to before. Okay, you take the magnetic fields in the lab and flip them, but the dual electric fields and flip them, right? When you do that, you find that, of course, the XY model is time reversal symmetric, but when you act on it with the fermion, you find that the Dirac fermion's Chern-Simon level flips. Okay? So you don't get back the original theory. What you get is a new theory. A fermion is dual to its time reversal partner. Okay? Since this was a duality, acting on it with time reversal should preserve the duality. And what we've concluded is that if I call this new fermion the time reversed fermion, it's dual to the original fermion. So while you do a calculation and you found a big Hall conductance, it's actually wrong, because at the critical point, the Hall conductance would also, it'll also be dual to a system with the opposite Hall conductance. So here, time reversal symmetry is not a microscopic symmetry, but rather some long wavelength emergent symmetry that you can't see from just inspecting the Lagrangian and doing simple perturbative calculations. Okay? So, yes, on the lattice constructions, you can show that this theory and that theory are related by some set of exact transformations. No, it hasn't been. Yeah, that was a long-standing confusion. Yes, yes. Let me give you. Let's see. I've already said this. Let me give you the sort of physics intuition for what this is, what this duality is. Okay, we have on one hand an XY model, and it's dual to a fermion. Okay, that's the fermionization. But this fermion is also dual to its time reverse partner. So we have a 3-member duality. And since the XY model is manifestly time reversal symmetric, there's no net vortices or anti-vortices. Okay? In the fermionic representation, the way you want to think about it is the fermion is a composite of the boson of the XY model and a vortex. If you take this object and you move another one around, you pick up a minus sign from the flux quantum. So this is a fermion. Is that clear to everyone? Okay. But since the original XY model is time reversal symmetric, I could have built a fermion out of a boson and an anti-vortex. So since time reversal symmetry flips the vorticity, right, this fermion becomes the dual fermion. That's the intuition. And this fermionized vortices since I won't have time, remember the last lecture I talked about my phenomenological motivations for studying these beautiful theories. This duality is what we've been using in our studies of the superconductor insulator transition. It turns out that the boson superconductor insulator transition is a fermion's quantum Hall to insulator transition. And the right-hand side are these fermionized vortices. This shows explicitly how the superconductor insulator and the quantum Hall to insulator transitions are related to one another. And the dictionary you want to keep in mind, or I keep in mind, is that the integer quantum Hall state of the fermions, of the fermionized vortices, is the superconductor, and the insulator of these fermions is the insulator of bosons. Yes? This one? That's a background. But we can do it, but it's also dual to the abelian Higgs, so that's also going to be true. Yeah. Not if the background is non-zero, right? If there's an external. Yeah, okay. I see your point. You have to make it slightly dynamical. Yeah. 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 Yes. Yes. Yeah, so they differ by irrelevant operators. I mean, you want to make it not fully dynamical? You want to think of capital A as a weak. Yes. Yes, that's correct. Yeah. It's a 3 plus 1D Maxwell photon. That's really what I think about it, which is essentially a moral. Yeah. Yeah, so if it's dynamical, you can integrate it out and then show that the spectrum of the two match. I'm not sure if it's an exact duality, but it's certainly true at one loop or something like that. So they may be differing by irrelevant operators. We can discuss it afterwards if you wish. Other questions? Now, let me come to this Fermion-vortex duality. I talked about boson-vortex duality. Now let me talk about the Fermion-vortex duality. We noted that the fermion theory is dual to its time-reverse partner because both are dual to the XY model. Okay? Because this is true, we can generate additional dualities by applying a set of these modular transformations. And when you do this particular one, you get the Fermion-vortex duality on both sides. And let me say what that is. So you do this transformation, you find on one side a free Dirac fermion with level -0.5, and on the other side you find something that looks like quantum electrodynamics in 2 + 1 dimensions. And you want to think of this in analogy with the boson-vortex duality. On one side we had an XY model, and on the other side we had a abelian Higgs model. In the fermionic analog of that is a free Dirac fermion on one side, and its vortex is a strongly interacting Dirac fermion, a quantum electrodynamics, QED3. Okay? And the way you see that this is a vortex, a Fermion-vortex duality, is if you differentiate both sides with respect to the capital vector potential, you notice that the Dirac fermion currents are related to the electric and magnetic fields of the dual quantum electrodynamic theory. So that's certainly consistent with all particle vortex dualities. But one thing you can see is that this mu is supposed to represent space-time. So if you look at the time component of this, it says that the density of these vortices is related to the external magnetic field. But now there's a 4 pi, which means we're attaching 2 flux quanta. Because if we had attached 1 flux quanta, we would have converted the statistics from fermion to boson. We don't want to do that. If we want to preserve fermionic statistics, we must attach 2 flux quanta. And that's what this 4 pi is doing. Okay? And so again, as I mentioned, in the quantum Hall context, this arises as composite fermions, where you can think of the left-hand side as electrons, roughly speaking, and the right-hand side as these composite fermions, which have 2 flux quanta attached to them. Now, we had shown that the boson-vortex duality and the boson-fermion duality can be exactly represented on a lattice. So suppose we didn't know about the boson-vortex duality. We only knew about the boson-fermion duality. Can we realize the boson-vortex duality as a member of this lattice? And the answer is yes. If you act on both with S, this S modular transformation, you realize that S acts like time reversal symmetry. It takes the original XY model and maps it onto the vortex theory. And it takes this fermion and maps it onto its time-reversed fermion. We know that this is a duality, and therefore this right-hand side must be a duality. And that's the boson-vortex duality. Yes?
In your lattice construction for Fermion-vortex duality,
Yes.
is 2 pi monopole operator?
So, OK, so let me tell you what we can construct. We can construct these S and T transformations on the lattice. OK? So I'll get back to your comment in a second. So while T is a harmless operation, it takes the partition function and multiplies it by a phase, just adding a level Chern-Simons. S is a horrendously violent deformation. You take the partition function, you introduce an additional variable, path integrate over it, and add this phase. So can we implement this on a lattice to make sure that we're not fooling ourselves? The answer is yes. And we did this recently. And what we actually did was we implemented this composite transformations, where we took the partition function and mapped it to this new partition function. And the idea was represent this new term as Dirac fermions living on a Euclidean lattice. One consistency of this is that if you do this and you repeat it with its inverse, you better get back to where you started, right? Because it's an invertible operation. What we found is that when you do this, when you do this twice, you get 2 Chern-Simons terms with equal and opposite signs. And each of them can be represented as fermions. Okay? And what we found is that if those fermions attract one another by the gauge boson and become superconducting, even though they're massive, if there's a superconductivity, there will be a Meissner effect that slaves the little a to big A. Because both of them see little b, and the little b acts like a glue. Okay? And if it gives them superconductivity, there will be a Meissner effect for the sum of little a minus big A, and that in turn will softly implement this Lagrange multiplier constraint. And this indeed we had checked doing quantum Monte Carlo, and we found exactly to be correct. Okay? So if we can implement such modular transformations on the lattice, we can in principle extend the boson-fermion dualities to other dualities on the lattice. Now please ask your question. Yeah. Yeah.
In the Fermion-vortex duality,
Yeah.
is 2 pi monopole operator, is it a physical operator in your lattice?
Yeah, so the monopole operator will be a fermionic operator because it comes from the flux. When you attach, even in the boson-fermion duality, right, when you attach flux to the boson, that flux is really coming from the fermions. Right? You can think of the Chern-Simons term as coming from the Dirac fermions. Right?
2 pi vortex or 4 pi?
2 pi in the boson-fermion case, right?
For the Fermion-vortex.
For the fermion-fermion case, it should be 4 pi, but I don't remember the details.
Yeah, so then
Yeah.
what is 2 pi monopole operator? Probably that exists in your lattice.
Yes, it does. It does. And in principle, you can give the 2 different fermions different masses, and then you can probably separate them out. But there will be gapped excitations. Yeah. I don't remember those details, actually. But in principle, yes, we can answer all these questions. That's the whole advantage of doing things on the lattice. Yeah. Yeah. OK.
What exactly is the lattice simultaneous for the S?
let's see, where did I do it? Here. Yeah, so we have the xy model partition function. Okay, say, if we're doing this on the xy model, it doesn't matter what we're doing this with. But this term represents these massive Dirac fermions hopping on the lattice. Okay? And you again arrange the microscopic masses such that the level will be exactly 1. And they couple to the difference of big A minus little a. Okay, so that's the way we do it. And if we want to do this twice, we have to introduce more species of Dirac fermions. It becomes more and more tedious, but it can in principle be done. So say suppose this is the first species, this would be the second species, and my point was that if species 1 and 2 attract one another because they're oppositely charged under little b, then you can form a superconducting condensate of them, and then that would Higgs out this difference. Well, if we have this and we have T, then we have everything, right? Yeah. You can reorganize your generators in different ways. It just happened to be more convenient to do it this way. Okay. So that's how you realize this part of the web. So if that may have been too fast, I wish to convey to you that at least that what we previously did was just here, and today we extended it much more. And some of this can be done on the lattice, and some of this hasn't yet been done on the lattice. This is a good place for me to stop and ask questions. I don't know how I'm doing with time. Should I stop now, or?
You've got 5 minutes left.
I've got 5 minutes left. So I think this is an appropriate point to stop on the pure theoretical physics. What I had in mind was to tie this back to my original motivational questions. But I can either skip that or relegate that to the afternoon session, whatever is more appropriate, depending on how hungry you are. And, huh? Do it now?
Yeah, we want to see the connection with the experiment.
All right. Okay. You're not hungry anymore. Okay, great. Okay. All right, but before I do that, do you guys get a sense of the things that we discussed so far? So there's a whole bunch of dualities. You can use them however you want to. They relate free particles to strongly interacting particles, so you have to be a little careful when we relate things back to experiment. Let's see how this is my thinking, okay? Suppose we want to talk about the quantum Hall to insulator transition. What we really have is a problem of electrons plus Coulomb interactions plus disorder plus external magnetic field. Good luck solving that problem. And the traditional approach has been to either neglect Coulomb interactions or neglect disorder, or something like that, to try to work directly in electron coordinates. The approach that we've been taking is to study the same problem in composite fermion coordinates using the Fermion-vortex duality. Okay? Now, since the composite fermions see on average zero field, the external field problem at least has been addressed. There are gauge fluctuations, which we have to deal with. That will be addressed by Coulomb interactions and disorder. And what you get at the end of the day is, instead of thinking of this in terms of electrons, you can think of this as a composite fermion metal, which is a diffusive, dirty metal that sees on average a very, very small magnetic field compared to the electrons. For the superconductor insulator transition, we've been using this, as I mentioned already, the boson. If you think about the superconductor to insulator transition in terms of bosons, that turns out to be a rather difficult problem. I particularly don't like bosons just because bosons are never free. If you want to have them to be stable phases of matter, you will always need to have strong interactions among bosons. By contrast, fermions, as we heard this morning when we described Fermi liquid theory, we have a free particle description of fermions due to the Pauli exclusion principle. We have a filled Fermi C, and others have spoken from the renormalization group point of view how many strong interaction effects get mitigated and weakened because of the kinematics of the Fermi surface. So if you can think about the same problem in a fermionic representation, I think you're better off. Well, if you have harmonic oscillators, phonons are good. Of course, that's why we teach harmonic oscillators. But luckily, they don't condense, right? Right. Okay. So let me just sketch, since I'm running out of time, what we're up to. Before we make contact with reality, we also have to take into account quenched randomness. Okay? And the nice thing is quenched randomness always involves some local operator. So you can have a random potential, random magnetic field. And we can use the ideas of duality to take the disorder Lagrangian and map it onto the dual disorder Lagrangian. For example, if we were talking about the Boson-vortex duality, if the original superfluid degrees of freedom were in a random scalar potential, the dual vortices would see a random vector potential. The reason that is because if you have a V of R couples to the density, since the density is the flux of the fluctuating vector potential, the V of R gives you a random flux, or a random vector potential, more generally. Okay? So you can map the disorder potentials from one side to the other. But now what I want to do is to say, remember I started my lecture saying I'm not against perturbation theory. I just like to do perturbation theory in the right coordinates. Once you find the right coordinates, do perturbation theory seriously and see where it leads. Of course, there's no rigorous justification for it. The hope is you can find an approximate set of results that are consistent with experiment. Okay? So we take Coulomb interactions as follows. The original electron coordinates, or the bosonic coordinates, it's a 4-particle interaction, right? It's a density-density interaction divided by Q. Again, in the dual representation, this becomes a flux-flux interaction. A sub t is the transverse part of the vector potential. And now you've converted a 4-fermion interaction in, say, a Landau level problem to a 2-gauge boson interaction in a Fermi C. Okay? While this still is very difficult, it seems to be easier than this problem. Okay? So whereas in electron coordinates we had Coulomb interaction, disorder, and magnetic field, in the composite fermion representation we have a dirty metal with a transverse gauge field with a 1/Q propagator. I don't know if you remember yesterday in Schenke's talk, he mentioned, or I think one of the speakers mentioned, that if you have a 1/Q bosonic propagator, it mediates a controllable expansion in deviations from the Coulomb potential limit. Yeah? Oh, I'm sorry. No, but at the end of the day, because it's curl A over Q.
Yeah, but then the Q will be in the...
Oh, in the numerator. You're right. Yeah, this is a typo. It should be in the upstairs. The propagator is 1/Q. Yeah. Yeah, but the omega squared will not be important. All right? So this, sorry, yes, thank you, Chenka. This should be Q upstairs, and the propagator is 1/Q. And then there will be omega squared, but we're going to look at next quantum corrections. So I'm going to take perturbation theory in these fermionic coordinates seriously. Okay? And when you do the mean field calculation, you find, what we found is that we get the right resistance at the quantum Hall to insulator transition. Okay? That's work that I haven't told you, and I can talk about it if needed, but this is what we've done in the past. But now what we want to do is correct the mean field approximation using the random phase approximation. And the result, what you find, is now we have to do serious perturbation theory in both disorder and the Coulomb field. What you find is that at the end of the day, you have these composite fermions. The disorder is a strong potential, a strong perturbation to them. They become essentially free fermions with a finite lifetime, as in any ordinary metal, okay, like a Fermi liquid, like a dirty metal. But the transverse gauge boson has Z = 1 scaling. Okay, the 1/Q comes from Coulomb interactions. There would have been an omega squared in the kinetic term, but that's becomes replaced by the much more important diffusive correction, which goes like I omega from the current correlation. So if you now look at this problem as a problem of metallic criticality, what we have is a much, I would argue, much easier problem to study, which is a free fermion, or sorry, Fermi liquid, maybe a highly renormalized Fermi liquid in these new coordinates, coupled to this Z = 1 gauge boson. So at the critical point, we have a natural story for why there would be Z = 1. Okay? And now this Chern-Simons gauge boson is overdamped, so it can, excitations can decay into it and out of it, and so it produces a dissipative bath for the quantum critical scaling. Now, to determine the correlation length exponent nu, what you have to do is deviate a little bit from the critical point. Then the composite fermion sees a small magnetic field, and then you have to repeat this calculation in a magnetic field to see how the spectral function of the gauge boson gets altered. Okay? And that will, in principle, give you nu z. But since we already know z is 1, it will give us nu. Yes?
What happens if you have sufficiently strong disorder so you cannot do MCA?
I don't know. This is with disorder and Coulomb interactions. Okay? I don't claim this to be an exact result, but I do claim this to be closer, as an approximately closer result than what you would do if you started with free fermions. You would get the completely wrong z, and you would get the completely wrong resistance. Okay? So what we're trying to do is now find approximate solutions based on duality rather than using it as an exact set of relationships. Okay?
SRP is controlled by large density of composite.
Yes. Yes. Like the density of composite fermions will be the density of electrons, say, at half filling, set by magnetic field, external magnetic field. Okay. All right. So that's the current state of thinking. So let me let me summarize the talk. I've talked about various types of dualities. I talked about 2 plus 1 dimensional dualities. I talked about boson-vortex, boson-fermion, fermion-vortex dualities, the duality web, and then my own particular obsession with this problem. Okay. Thank you.